Welcome, fine physics folk. We've spent the last week and a half reviewing main concepts behind Newton's laws and going through some of the basics of inclined planes, which was one of the 6 simple machines that we took notes on before our break. Now, the inclined plane was the first of the simple machines that I wanted us to look at, and we didn't do everything I wanted to do with the inclined plane, but for purposes of time and understanding the calendar and what's going on right now, I'd rather you get exposed to the general concept of the 6 simple machines rather than trying to get lost to the minutia of the complex calculations of just one or two. I feel like it's going to be more useful for you to know more about all of them than a lot about one of them. So, here we go, moving on to levers. A lever is simply a rigid bar that pivots about one point and is used to move an object at a second point by a force applied at a third. Okay, that definition sucks. It's tough to understand what that's actually saying. Let's examine this picture though. A seesaw is a great example of a lever. Let's break this definition down. A rigid bar, okay? That's the actual seesaw itself, okay? So there's your rigid bar. Rigid bar. Okay, great. That pivots about one point. Now, pivots is a word that I don't necessarily expect you guys to know, but this is going to be called the pivot point. Right there. Pivot. It's where the seesaw itself can rotate up or down. That is used to move an object at a second point. So here would be the second object, and here would be the third object. So we can kind of imagine how this can work. You've got 2 people and the pivot point. So those are the 3 places that it's talking about in its definition. And then the lever or the seesaw can move up or down depending on the forces applied to it. So this is what we're going to kind of examine a little bit more. I want to be clear about the parts of a lever. So we have the beam, which was the rigid bar. The pivot point is known as the fulcrum. This is an important word. I'm going to be throwing this word around a lot, and I need you to understand that the fulcrum is the pivot point, or the point of balance, or the point of rotation for a lever. That is the fulcrum. Weights on a lever are often referred to as loads, and effort would be any external push that is added to the lever. What we have here is you could kind of see a situation as follows as to how a lever is useful. What we have here is an example of how a lever is used. We have the pivot right here. We have the woman pushing down right here. So here's one of the forces. Here's the second force, the load. As she pulls it down, the bar is going to pivot and move the rock up. So as she pushes it down, the rock will move up. We can kind of imagine how that would rotate. But the cool thing about a lever is it can amplify the force that you exert. If you notice, there's another term called a lever arm right here. This is the distance between where she pushes and the fulcrum. And that's going to multiply the force that a lever can exert. We're going to see that in a little bit. There are 3 main types of levers. It depends on how you arrange the fulcrum, the force, and the load. That's it. So the most common lever type that we're going to use is the first class of levers. First type, first class, interchangeable ways of describing it, where you have the fulcrum in the middle. You have the fulcrum in the middle. You push down on one side, and the other side goes up. Examples of this type of lever would be here. It says a saw, a crowbar, an oar in a boat. I like to think of this as the top of a soda can. This is a great example. Technically, that's a lever. When you pull up, if you think about it, you have a greater distance of the side that you're pulling up. The shorter distance, the other side of the lever, is pressing down. And because you're pulling up a greater distance, the other side is pushing down with a greater force. And that's why it's literally able to rip metal apart. And that's how you open a can, by taking advantage of a lever. That is a first-class lever. The second-class lever is where the load lies between the pivot and the point of effort. So the biggest example of this is like a wheelbarrow. So if you look at the wheelbarrow, the fulcrum would be the pivot point. What you're holding, the load is right next to the wheel practically, and then you're lifting it further up. So we're not going to pay as much attention to class 2 and class 3 type levers. I just want you to know they're out there. What it essentially means is you can lift the heavy load with less force because your arm would be further out from the fulcrum. And conversely, the third type of lever is really good for working out, where the load is further away from the added force. What this means is it requires more force to lift a set amount of weight. What do I mean by that? So if you pick up a weight and you just hold it by your side, it's not that hard to hold. Well, depending on the weight. Let's just say a 10-pound weight. But if you lift that weight so that it is horizontal to your body, and then your arm is parallel to the ground, that weight isn't any heavier. But what happened is you changed the positioning of your body to form a lever. And now that weight isn't heavier, but your arm is experiencing more force because your arm has turned into a lever. So here is a word that is going to mess everybody up. Torque. A force that causes rotation. So what do I mean by that? One, this is a simplistic definition of torque. Maybe you've heard of torque in terms of a car. It's absolutely applicable in cars. Maybe you've heard about torque is like, oh, I twisted my arm, I torqued it pretty badly. So anything that has to do with a rotation is a torque. So how does torque or rotation or circular motion apply to levers? Well, let's look at this. Here we have a picture of a lever. So here we have is the fulcrum. All right. Okay. Let's just say I put a weight right here. Gravity is, of course, pulling that weight down. That means the lever would go down. Now imagine that the lever was attached to the fulcrum. And let's just pretend, let's just imagine that it didn't do anything, like it didn't hit anything. And if it was allowed to freely rotate, what would happen would be this thing, this whole object, would enter circular motion. If this was just pivoting around the center point, I hope that you can see how this could turn into circular motion. It would actually cause the lever to rotate clockwise because you have more clockwise force, more clockwise torque than counterclockwise torque. You currently have 0 counterclockwise torque and all your torque is clockwise. Okay, that's a little confusing. Let's look at it this way. In order to balance, the torque on each side of the lever must equal. And here's the equation. Torque equals F times D. Torque, and that's the Greek letter tau. We're not going to really get into tau. It's tau. It looks like a J, but it's not. It's the Greek letter tau. I don't care about that. We can just write it as torque. Torque equals force times distance. The force in this equation is the weight. Mass times gravity. Mass times gravity. All right? And D is the distance from the fulcrum. I want to be as clear as I possibly can. This is the concept that a lot of people are going to mess up when doing levers. D is the distance from the weight to the fulcrum. D is the distance from the weight to the fulcrum. So, here is my question. Torque is force times distance. So I put, let's just pretend, all right? I put a 4 kilogram weight there. And then I put a 4 kilogram weight here, okay? We have the same weight on both sides. Bizzuto, isn't that mass? Yeah, we could just multiply it by gravity. It's going to even out. So for these, you can use masses. It's going to kind of be the same thing, but I want you to know technically the torque equation is force times distance or weight. In all the problem, we're going to see masses, but if you just multiply these numbers by 9.8, that's how you turn them to the forces. It's not important that we do that right now. We have 4 kilogram here, 4 kilogram there. Okay, your gut reaction says, okay, if I have the same weight on both sides of the lever, if I have the same weight on both sides of the lever, it should balance. But no, even though the weights are the same, the torques are unequal. What do you mean by that? Well, what's the torque on the left side of the lever? The torque on the left side, so left side of the lever is the force, we'll just call it 4, torque equals 4, and it is 4 distance units away. So the torque is 16 on the left side of the lever. On the right side of the lever, we have to calculate the torque here. Torque is 4 times, and it's only 2 distance units away from there. So here we only have a torque of 8. Let's not even worry about the units for torque. It's joules, but we don't care about that right now. All I want you to understand is how this is working. Which side, the left or the right, has more torque? The left side has more torque. That means that the force pushing down here, the torque, is going to be greater than this, which means this is not balanced. One side is going down and one side is going up. If this was to spin, the left side would be going down because it has more torque. So if this were to spin, if we would assume that it's free attaching, this would spin in a counterclockwise spin. Counterclockwise. Why? Why is this counterclockwise? Well, the side with more torque goes down. We said the left side is more down. So again, if from here, if it were to spin in a circle, look in the direction that I'm making the circle. That is counterclockwise. When I say counterclockwise, I mean moving in the opposite direction of the hands of a clock. That's what counterclockwise means. So answers are going to be clockwise or counterclockwise. And remember, d is the distance from the weight to the fulcrum. Okay, so clear all that out. D is the distance from the weight to the fulcrum. Here's my next question. Is this going to rotate or is this going to balance? Well, let's take a look. If I go ahead and put a 5 kilogram mass right there at the 6, let's just say it's on the 6, and then I put a 15 kilogram mass on the 2, okay? Let's see. So if it balances, the torque on one side, on the left side, should equal the torque on the right side. So this is going to be 5 times 6. If it balances, it will equal the torque on the other side. 2 times 15. Oh, 5 times 6 is 30. If it equals, it's balanced. No rotation. It's totally balanced. No rotation. Or balanced. Yes, the torques cancel out. The torque is equal and opposite. Those counteracting torques cancel each other out. So this is the essence behind a lever. If you have more weight at less of a distance, it could be, if you have more weight right here at less of a distance from the fulcrum, it could be counteracted by a smaller weight a greater distance from the fulcrum. This is the essence behind levers. And I want to be very clear. I was just Googling some images of tools to kind of get ready for this, and I found this picture, and I couldn't help it. I had to include this in the little presentation. So here we go is our 3 set wrenches, and it says standard, high torque, and extra long. Why is this one high torque? Well, torque is force times distance, okay? If you're turning it with your hand, you're going to exert the same force. You can't get stronger. It's not like if you pick up a different tool, you get stronger. But if you look at it here, and if you press it at the end, you have a larger distance than you would with the standard size wrench. And with more distance, you can have more torque. In fact, the longer the wrench you have, the easier it is to screw and unscrew things in. So extra long is a new size, kind of came a little bit later. This actually would have the most torque, because if you look, most torque. Because if you look at the distance that this tool is providing, and if you don't believe me, if you have a wrench at home and you can screw it, if you can tighten and untighten things, try holding it at different points of the wrench and see if it's easier or harder at specific ways of holding it. Okay, now, what type of questions am I going to ask you about this? Look at this setup right here. Will this lever rotate clockwise, counterclockwise, or will there be no rotation at all? Okay, all right, let's find out. So, if we're going to do this, we have to see the torque on the left and the torque on the right. What is the torque on the left? The torque on the left is going to be FD, 4 times 6. All right? Equals, put the equals under the fulcrum. On the right side of the lever, it's going to be 3 times 8. All right? So 4 times 6 is 24 equals 24. Because this is a true statement, because the torque's equal, we could clearly say this one will have no rotation. It will balance. But what about this? Aha. So, I don't know. Let's find out. If it was to balance, they would be equal. 3 times 5. Does that equal 4 times 3? Well, okay. I think this is obvious. 15 does not equal 12. That means it is not balanced. So we know it's not this one. Now the question is it clockwise or counterclockwise rotation? Well, the left side is a bigger number. If the left side is a bigger number, that means this arrow going down is bigger, and it's going to dominate the rotation, meaning it's going to rotate like this. So that would mean if the left side is bigger, you would get counterclockwise rotation. If the left side is bigger, you get counterclockwise rotation. Left side is bigger. If the left side is bigger, you get counterclockwise rotation. All right, let's see this next one. Look at this. Wait, we've never seen something like this. So what we're going to do is we are going to add the torques independently. What do you mean by that? So this is what you're going to do. You're going to set it up. And underneath the fulcrum, I'm going to put the equal sign. We're going to go ahead and just set it up like this. Every weight gets an FD. Every weight gets an FD. Every weight gets an FD. Again, Bazzuto, why are we using F, force with these masses? If I just multiply them all by 9.8, I'm not changing the answer. I'm just changing the numbers. But mathematically, they would be the same thing. So take a look at this. All right. D is the distance from the weight to the fulcrum. So here the weight is 2. The distance is 6. 2 times 6. Good. All right. Here, the weight is 10. And the distance is 3. Nice. Bring down the equal sign. Here, the weight is 4. And the distance is 8. Okay. Okay. Let's see where this goes. 2 times 6 is 12. 10 times 3 is 30. Does that equal 4 times 8? What is 4 times 8? I don't know. 32 maybe? Something like that. So 42 does not equal 42 does not equal 32. Meaning that it's not balanced, not that one. The left side is bigger. If the left side is bigger, it means counterclockwise rotation. If the right side is bigger, that would mean clockwise rotation. All right? If the right side is bigger, it would mean clockwise rotation. If the left side is bigger, it would mean counterclockwise rotation. Now, your homework, your assignment is going to be to get a lot of trophies in the physics classroom. I am assigning you 2 sets of problems of trophies to get because these problems are easy once you get the hang of it. But here is a copy and paste of an exact question. If you have this, is it going to rotate clockwise, counterclockwise, or no rotation? Now, this is a more practical, real-world explanation. In those sample problems that we were doing, it was really simple. But I want to stress to you that d is the distance from the weight to the fulcrum. All right, so we have a fulcrum. It's right here, pivot point. So we have F, D, F, D. All right, so if it balances, they will equal. If it balances, they will equal. Well, let's find out. The force for this first one is 8. What is the distance here? I know your gut reaction is going to say the distance is 30. It is not. It is at the 30 mark of the meter stick. But if you look, each of these little tick marks is 5. How many centimeters, meters, whatever unit of distance this is, how many is it from the weight to the fulcrum? That is actually 5, 10, 5, 10, 15, 20. Or 50 minus 30 is 20. The distance is 20. D is the distance from the weight to the fulcrum. D is the distance from the weight to the fulcrum. This is what is going to mess people up. Okay, now let's look at the right side. The right side has a force mass of 4. What is the distance? Don't say 80. It's not. D is the distance from the weight to the fulcrum. D is the distance from the weight to the fulcrum. That is 30. Do you see? We got the force and we multiplied it by the distance. We got the force and we multiplied it by the distance. D is the distance from the weight to the fulcrum. 8 times 20 is 160. 4 times 30 is 120. They are not equal. And this would result in counterclockwise rotation. There you go. That's all there is to it. Archimedes is famous for coming up with a saying, give me a lever long enough and a fulcrum on which to place it, and I shall move the world. These principles of levers have been discovered from ancient times. But these relations, these understandings of how you could go ahead and multiply the force by increasing the distance, several scientists for fun decided to calculate if you were to weigh like 150 pounds, how long the lever would have to be in order to go ahead and move the world. Maybe we'll do that calculation at some point because we know the mass of the Earth. We know the mass of Archimedes. Perhaps we could calculate the distance out. It would go to balance the Earth. Nevertheless, Understanding how levers work is an incredibly powerful tool. Look through the homework, look through those assignments. Please email me if you have questions, and I want you to get all 7 trophies by tomorrow night. Good luck, and I will see you guys later.